Okay, welcome people of the pre-seminar. We are very happy that we have Michael Heins, formerly from Würzburg, now from the south of Italy, and he's going to tell us about entire functions on Lie groups. Please.
Thank you, and thank you for this opportunity, even though it was very spontaneous. So these slides will be a bit experimental, but I think I've landed on a version that's not horrible. So maybe a bit of background. So I've done a bunch of differential geometry with Stefan, but also I'm a complex analyst. So I have two advisors. So there will be kind of weird mixture going on. And let me get started. No, I don't jump in right away. So what I will tell you about today is about the function algebra, namely the entire functions on a Lie group. And I cooked this up or dreamt this up one morning during my master's. So long time ago, like 5 years now. And we were working on a problem in strict deformation quantization. And well, we kind of needed the right observables. So subalgebra of the smooth functions, that was particularly nice. And I just wrote down that definition. I will show it to you in a moment. And then I spent the rest of my PhD understanding what they really were. Okay, I did some other things as well, but this took a while and there was quite a bit of resistance. And yeah, this is the journey I want to kind of take you through in this pre-talk. So let's get started. I will show you a formula that I quite like. It's the Lie-Taylor formula. And okay, this sounds like more than it is. This is really just the Taylor formula in a particularly nice chart. Namely, if you have a Lie group, so a smooth manifold with a group operation such that the group operations are smooth, then well, you get an exponential, a Lie exponential from the tension space at the group unit, which is the Lie algebra, to the group. And this turns out to be a diffeomorphism, at least in a small neighborhood of 0 in the Lie algebra, which is a vector space. So you get to build charts from this. And these charts are actually real analytic. So you might know the statement that every smooth manifold has a real analytic structure. And in this case, this comes in a very concrete way, the one you would have written down anyway. That gives you analytic charts. So if I now take an analytic function phi on G, some group element, which I think of as the expansion point, and well, I want to perturb this expansion point by something small. Small things are exponentials of Lie algebra elements. So this xi should also be sufficiently small. Then I can compute the value of my function at, well, G perturbed by exponential of xi by means of this exponential operator. So if you stare at this for a while, so this Lie of xi for me is the Lie derivative in direction of the left invariant vector field associated to xi. But if you work with these things for a while and put everything into indices, you will go insane. I did. I've recovered since, but don't do that. This notation is better. And what do? Well, you differentiate k times in direction of xi, and then you evaluate at the expansion point. And sum over this in an exponential fashion. This is the Lie-Taylor formula. Proving this is as easy as, well, realizing the left-hand side is precisely a coordinate expression of phi in the exponential chart around G, and then, well, just plugging in the Taylor series for this composition. This is all you have to do. Nevertheless, this is useful and this is nice. I wasn't aware of this when I wrote down the definition, but yeah, we will see in a moment that this resembles it very much. And okay, first a small kind of trick from complex analysis. I can introduce a complex parameter on the right-hand side, just, well, essentially rescaling my xi. So I think of xi only as a direction now, and this z is kind of this magnitude and the phase. This still makes sense. So the series doesn't really care about complex multiples, and so I get a kind of holomorphic extension of my phi to something bigger, whatever that may be. And what that may be is kind of the crux of the whole business. Anyway, we needed a stronger condition. And for this, we should take a look at the multivariable version. So God forbid, we choose a basis E1 to En of the Lie algebra once and for all. And then we can expand our xi in this usual basis way. And then you can just plug this in for the xi and you can multiply out. So multiplying this out essentially in the universal enveloping algebra of your Lie algebra. If you want, this is really what is happening. So you can extend this Lie algebra representation, taking Lie derivative to an algebra morphism of the universal envelope, and then you just multiply out. And what this gives you is a kind of a multivariable version, and I've written it down in a non-commutative fashion. Every Taylor formula should be written down in this fashion, even the one you learned in calculus. They did it wrong. So what do? You just get derivatives into any combination of k derivatives, any order, but you really have to take all of them and you sum over this. The version in calculus, which you know, first of all, this can be derived this way, really useful. So if you have to give a calculus lecture, this is how you should do it. One variable is all you need to understand. And secondly, the commutativity of partial derivatives. So if the group is abelian, these Lie things just turn into partial derivatives, then gives you some repeating terms, and that's where the stupid combinatorics comes from that nobody wants to really figure out. Okay, so this is the multivariable Taylor formula, and this brings us to the definition. So what we needed is, okay, first of all, it's an observation, this I should mention. The coordinate expression of phi, if this happens to be entire, so there's a radius of convergence of this power series here is infinite, then you get some sort of Cauchy estimate on these Lie derivatives, and you can differentiate this expression up here by z and set z to 0 to extract your derivatives. And you can do the same in the more complicated case. This is sometimes very useful. This is why I want to mention this. Okay, nevertheless, that's the following definition. Entire function. What do I want? Well, I want that the series here, so I've kicked out the one variable version, this one you've seen just now, to converge absolutely. So I want to make sure that all kinds of Taylor series are convergent. And I need a bit more. It would be sufficient to have absolute values kind of here, outside of the summation. And that would give me convergent Taylor series, and that's actually equivalent to the condition I wrote in the line above. I need more. What I need is that after putting the absolute value all the way inside, so kind of killing all kinds of cancellations that can happen, and this can be a lot. So I can construct Lie algebras where these cancel quite a bit. And, well, nevertheless, I want that this series here, so you have a polynomial growth here, this is what's left of the xi, the components of xi, just condensed to one variable. And then in here, these Lie Taylor coefficients, this is supposed to be summable. And that's a horrible technical condition. If I give you a function, checking this is pain. And in fact, it took me, I think 3 months still during my master thesis to figure out whether there's an example. So I called these functions possibly trivial at one point because I couldn't find non-trivial examples. Turns out, good news, they exist. If you have a representation, you can go to the matrix elements or representative functions, if you know what that is. These are always entire. So representation on a finite dimensional space. So in particular, if your group is compact, there's a wealth of these. Okay. And okay, this defines me algebra, and okay, these guys are actually semi-norms. So I can endow this with a locally convex topology, and we get a Frischi space. So good news. This thing is useful, and even better news, this solved my problem. And what then was the kind of issue is to actually describe this, to work with this, to find out what these mean. I didn't know about the Taylor formula. This important bit. I had no clue the Taylor formula existed when I wrote down this condition. I just looked at the star product.
There's a quick question.
Yeah, so of course, go ahead.
Sorry, can you hear me?
Yes.
Yeah. Just wondering if the radius of convergence you're using, this R, is supposed to be uniform.
So this is
over the group.
Any R. So every single R gives you a seminorm, and I want these to be finite for all of them.
But
so this radius is infinity.
But you're using this R at which point of the expansion of phi? Only at the identity or at other points as well?
Okay, you can do this at the identity, and this condition is strong enough that you get the same thing regardless of where you expand. This is why I can put the group unit on the right-hand side here. So the condition with
surely
the absolute...
there are functions that converge on radius r, but have a pole right outside of that.
This is why I have all the r's here. So I prevent these poles.
I see. Okay, so that's
so the space
condition.
depends on the choice of bases. Otherwise, you don't. This r is meaningless because you can always rescale your bases.
Okay. Okay.
So intrinsically, having one r such that this converges is a good condition. This is just being real analytic. And having all r is again interesting because that doesn't depend on the choice of bases again.
Okay, but if your g is Rn, this condition is stronger than just requiring for the function to be entire on Rn.
It's not if it's Rn, because then this non-commutativity here doesn't happen. So
no, but I mean, if you have a function that has a pole only outside the real coordinates, it's entire on the real.
No, it's not. The series will not converge.
It will not converge, exactly. But that function is entire on the real.
Okay, I call it entire only if it's extendable to all of C.
I see. Okay, all right. Thank you.
I really need this. So these poles that are hidden away in some sort of complexification are precisely the problem. This may not happen. But thank you. Okay. Good. Then I think I continue. So what's the objective? What did I want? Well, I wanted to realize this algebra here precisely because in the vein of this question as a restriction of a good holomorphic object on some sort of complexification. Okay, that's a wish, and that was a wish for the longest time. This was not clear what the GC might be, and this is where I want to go now. So we first of all have to find out what kind of complexification we want to use. This is not at all uniform, and it depends on the problem you're looking at. And well, the important bit for me as an analyst, if I want to extend functions, is that I get an arrow. I need a group morphism from G into GC. Otherwise, I cannot restrict. And okay, if this thing is injective, that would even be better, but at least I need an arrow. And many classical, more algebraic notions of complexifications don't give me that arrow. So we had to go looking, but some smart people have thought about this. And in the end, there is a notion that works. But let us maybe think about what our complexification would be. So we addressed this to Sophus Lee, because he invented Lie theory, and we like that. So what's our wish list? What if we could dream up something? What's the best we could hope for? Well, first of all, so I want the thing to exist. That would be good. And I also want it to be, well, unique up to isomorphism, group isomorphism, that would also be good. And, well, even better would be functor reality. Again, we're being greedy right now. We're in dream wish land, so I will wish for the best thing. So what do I mean by this? Well, I don't just want to complexify a group, but also arrows. So if I have a group morphism between two real Lie groups, I want a holomorphic arrow between the complexifications. And okay, in particular, I want existence and the categorical proper version of uniqueness. Moreover, well, what do I want? Well, I already know how to complexify vector spaces, namely just tensorizing with C over the reals. This gives us a vector space complexification that is very well motivated, and I kind of want to keep that, even when I view the real group as a complex one. And a bit more general, well, I have my Lie group, I get its Lie algebra, then the Lie algebra of the complexification, well, that should be the complexification of the real Lie algebra. That would be nice, and in fact, this is also how you can start or kick off construction of the complexification we will use. Well, and wishing for more things, this I've already touched on. I want that G sits inside of GC. So the best thing one could hope for would be an embedding. So really as a submanifold, not just immersed, but really as a real nice submanifold in the complex group. That would be cool. Too cool to be true, but cool. And finally, and this is again something where the complex analyst comes through, I want an identity principle. So again, think about the problem. You want to extend functions. It would be good to not add any superfluous points. So I want an identity principle. The real locus should tell me how my function behaves. If the function is 0 on the real group, whatever that image may be, it should just be the 0 function. Otherwise, extension becomes, well, not meaningless, but then I've kind of a choice, and I don't want choices. Choices are bad. Okay, so that's our wish list. And the construction and the definition is now motivated by mostly the functoriality. And this goes back to Hochschild in the 60s. So he worked with Chevalier, and they, well, cooked up the following universal property. So he was a doctoral student of Chevalier, actually. So what do? You start with your Lie group G, and you want the following. Given a complex Lie group H and Lie group morphism phi, so this is morphism of Lie groups now because G is only real, not complex, I want to be able to extend this. And so the universal complexification is a pair. I get my arrow, the arrow I wanted, from G to GC. Again, a group morphism, a real Lie group morphism, so smooth. And, well, GC should be a complex Lie group. Otherwise, the complexification name would be stupid. And the property is then, I want a unique holomorphic group morphism. So there's different types of arrows in this diagram. Be a bit careful. That extends my phi in the sense that, well, this diagram better be commutative. So the pullback of phi c should be the phi I started with. First observation, so this puts representation theory at its core. The phi can be just a representation of G on a vector space, a finite dimensional one, which is in particular a group. Then, the general linear group of the vector space, rather. And then I can complexify this to a complex or holomorphic representation. And that's what the two were after when designing this gadget. And in fact, this works really well. So we will see this universal complexification always exists. And then you get a translation of real representation theory of G to holomorphic representation theory of GC. And, well, irreducibles go to irreducibles, the weight is preserved, the list goes on. This is actually really, really nice. They solved what they wanted to solve using this, but okay, it's also useful in other regards. Anyhow, let's check in on our wish list. Did we get coal or did we get candy? It's a mixed bag. You have to be careful. There's some coal in there. I tasted some. So again, I've just copied what I had on the other slide, and we just go through it one by one. Okay, it's functorial. Life is good. So going back to the diagram, the uniqueness is obvious to everyone who has done a single diagram kind of uniqueness proof. This is nice. The other thing which I mentioned with, okay, I want to complexify morphisms between real groups. This is also easy. So if this H is only real and I have a phi, I just post-compose with the eta corresponding to H and apply this diagram, and I get what I wanted. So functoriality, check. Life is good. About vector spaces, mixed bag. Good news, complexification of a vector space as a group is, again, the thing you would expect. So the complexification as a vector space. But the Lie algebras might be funky. So it may happen that the complex dimension of the complexified group is strictly less than the real dimension of the original one. This confused us for a while. So at the start, I didn't believe this could happen, and until I found this inequality in Bourbaki. They don't give a counterexample, they just state the inequality, prove the inequality, and move on. So yeah, I was a bit of looking for the counterexample, but there's a quite nice one using SL2R and its universal covering group. I will come back to this example later, which, I found this in the book by Joachim Hilgert and Karl-Hermann Neb. You should read this book. The Lie theory book is amazing. I use it as a microphone stand right now. It's versatile as well. Okay, moreover, let's keep going. So this injection thing, yeah, if the dimension drops, then this injection also kind of screws up. But the good news is that you lose a real dimension and a complex dimension at once. So you don't get some weird directions you cannot control. Just you might end up dropping one that was there originally. So extension is still on the table. This is the good news. And what's a really useful observation is that this eta the image of G is a closed submanifold, actually, because it is the fixed point set of a complex conjugation, which you, well, looking at the construction properly, you see you have a choice at one point which direction is holomorphic and which is anti-holomorphic, and that gives you, in the end, an anti-holomorphic conjugation. And the fixed point set is precisely eta of G. So you can work with this group instead. And in particular, this is kind of nice, this is now really injectively embedded in GC and fulfills the universal property. You can just check that. So what you're really complexifying is eta of G and not G itself. That is a useful technical intermediate step if you want. Okay, but in the end, we have some more good news. The identity principle works precisely because the aforementioned deleting of matching directions. So their life is good. Okay, I have to speed up a bit, but fine. Finally, one proposition that I've found nowhere in the literature, but I'm sure people knew this. So the pi1, so the fundamental group of GC, is at most as complicated as the fundamental group of G. This is important because, well, I want to extend functions. I have already kind of forced the Taylor series to converge, but that's not enough. There might be a topological obstruction, so think of the usual logarithm on the complex plane. If you go around 0 once, well, you're off by 2 pi I. That's bad. Don't want to do that. And this essentially says that the topological obstructions, if I start with a function defined on G, are already all fulfilled. There is no obstruction anymore. There's nothing new happening in GC. We will see this in some examples in a moment. Okay, but I will give you a brief overview of how to construct this for compact groups, because I know some people in the audience are interested in Hopf algebras, and this is a very nice application. So we take a compact group. This has to do with, well, I want some faithful representation to have a subalgebra that's not too small, but we go to the continuous functions on this group. You can also do this on a subalgebra. It doesn't really matter, but the point is you get a coproduct, a co-unit, and an antipode. The important bit is the coproduct. So what does this do? This takes a function of one variable and gives you one of two. So this is, I will not tell you why this isomorphism works, but trust me, there's a notion of tensor that does precisely what we want. And, well, how do you do this? You just look at phi of G times H. So you use the group structure. And in the end, you reverse this process to get back group structure for your complexification. You kind of need this. Anyhow, so co-unit and antipode aren't as important. I just included them for completeness. And what do you do then? Well, this is a Hopf algebra, and it's a star Hopf algebra. So you have a star involution, just complex conjugations borrowed from C. And what you can then prove, and this is a nice little exercise in Hopf, but it's not even Hopf theory, it's just differential geometry, is that the real star characters of this algebra here are precisely the delta functionals corresponding to points of G. Here the real bit is important. And okay, this is essentially Milnor's exercise, if you've heard of this before. So any good differential geometry course will have you do this exercise. And the idea that Chevalier had then was, well, I can look at complex characters. This is fine. And this gives me, again, a group, so that this is a group, uses the co-multiplication, and the complex star characters then give you a realization of this complex Lie group. Okay, you have to build a topology here, so this is not completely trivial, but it's a nice kind of exercise, or maybe a bachelor thesis, I'm not sure. Some of this is kind of annoying. Okay, good. So that's the construction for compact K, but the complexification, the universal one, exists in general. I will just briefly mention, so what do? You start with a simply connected group and a connected one. So go to the universal covering group, which is just the universal covering space, which happens to be a group if you start with a group, just by lifting all operations. And then you quotient out, so you complexify this by Lie 3, because you can take the complexified Lie algebra, and if you use a holomorphic version of Lie 3, this gives you really a complex Lie group. And then you quotient out kind of the redundancy, which is, well, the image of the pi1 of G, just as you can realize as a subgroup of the universal covering group, push it to its complexification, take the smallest closed subgroup containing this guy. This is where you lose dimensions. And then the quotient does what it's supposed to do. The construction can also be found in Karl-Hermann Nips and Joachim Hilkert's book. Okay, or in my thesis. I wrote it down again. And finally, the disconnected case. Okay, this is then easy. The connected components, the component group here, this shouldn't change. It's a zero-dimensional group. Okay, if this is real or complex, you tell me. I don't care. This doesn't change, and then you get a nice commutative diagram together with exact rows, and but this has a unique solution in the end where you place the complexification in the middle. Okay, so that's kind of the construction, and some brief, quick examples, so I don't go over time. So let's be quick. Okay, this I already mentioned. A bit more interesting. If you start with U1, so this kind of the unit circle in C. This is a nice abelian Lie group, and complexifying this gives you the cylinder. So C without zero. And the way you can think about this is you start with polar coordinates. The original U1 is just the angle, and the complexification now also has the radius. And in fact, you can prove this for any compact Lie group. There is a polar decomposition that does precisely what it says on the tin. The new directions are always just vector space directions, so this kind of scaling by R. And so you see that the topology doesn't change. So this theorem about the pi1 I showed, this is really obvious in the compact setting. And in particular, also important, the complexification of a compact group is never compact, only if you start with a zero space. This may happen, but okay, if it's interesting, things are actually happening. Then kind of the lab rat, if you complexify SL2R, which remarkably is not simply connected, so there is a pi1 here, you get SL2C, which is simply connected, no more pi1. So you see the inclusion I had can be strict, and if you take the universal covering group of SL2R, again, you complexify to SL2C. So kind of the budget version of my proposition says if the original group is simply connected, so is the universal complexification. And that bit is obvious. That is very easy to see from the construction. From the construction, the second one, not the Chevalier one. Okay. Finally, so kind of to illustrate that this non-uniqueness can be quite severe, if you start with the orthogonal group in signature PQ, then well, you just wind up with the orthogonal group in no more signature, just P plus Q comma 0 if you want. And okay, this is also just for illustration. If you start with kind of P plus Q comma 0, which is this, you still get P plus Q in the complex setting. So real forms are not at all unique. And that's fun because you can port functions from one to the other, kind of by extension and then restriction. Anyhow, this is the examples I wanted to cover. Let me very briefly give you the theorems I showed, so kind of a resolution of this whole wish extension restriction thing. So we're going back to entire functions now. So if I start with an entire function on G, I have this power series, and while the condition I posed is strong enough to continue analytically along any path, this gives you, first of all, extensions if there's no monodromy. And then, well, it's an idea by Stefan, if you start with a function on G, you may first of all lift it to the universal covering, extend from there, and then because, well, the lifting, this is periodic with respect to pi1, the resulting extension is still periodic because of the identity principle. And so it descends back to GC, and that gives you this theorem. So I get to extend entire things to holomorphic things without any assumptions. Well, G is connected. Otherwise, this doesn't work, of course. Okay, some bad corollary. The entire functions on this covering space of SL2R, they're no longer point separating. Just like representations on finite dimensional spaces, they are automatically periodic with respect to the pi1 of G. Because essentially, if you look at this complexification again, the eta for this guy is just project down to SL2R and take the eta, which is just the inclusion of, well, real matrices are also complex matrices. Okay. Another theorem, the other way around, the restriction theorem. So here I have another technical assumption, namely that the group is linear. So I have a faithful finite dimensional representation. Then any holomorphic function on the universal complexification. So again, globally defined holomorphic function, generalizing what we wanted to generalize, gives us an entire function on G if I pull back with the morphism eta. The linearity here, I don't think it's necessary. I can't produce a counterexample, but I also can't prove the general theorem. So what I use the linearity for is to use operator norms, because then you get that the operator norm of e to the power of xi is at most, well, e to the power of the operator norm of xi. So you have kind of a Lipschitz estimate for the exponential mapping, and moreover, it's compatible with group multiplication. This I haven't managed to generalize yet, but I think this is very much possible. Okay, putting everything together, and then I can wrap up, is, okay, I can kind of do the round trip. So I can first extend, then restrict back, or vice versa, and I can also look at the topologies. And the upshot is, this closes nicely, this works very well. So again, under this linearity assumption, I get that this pullback, so precomposition with eta, is an isomorphism, so bijection, which is compatible with pointwise products and addition of the Frechet algebras here. So this guy gets a Frechet algebra structure by means of the seminorms, which, well, gave me the condition and the definition. And the holomorphic functions on GC, well, they are just locally uniform convergence. So really, really the natural topology of holomorphic things. And in fact, it's one and the same. So the funny topology I wrote down after sleeping badly or well, depending on your taste, well, turns out this is just really holomorphic things. And this then also provides more examples beyond the ones we already had. And it provides all of them. Okay. That is, I think, what I wanted to say. So we're at the last slide, and I'm 2 minutes over time. Not too bad. Thank you very much.
Okay. Thank you, Michael, for this nice talk. Are there some questions?
If you could go back to the Hopf algebra.
Of course.
Of course, yeah, the Hopf algebra is
You can expose me now as someone who doesn't know anything. Go ahead.
Are you sure that this is a Hopf algebra? Because I guess the tensor product you have, you mentioned this quickly, is a completion of the vector space tensor product. So then it's more a compact quantum group than a Hopf algebra.
Okay, I cheated here because I didn't want to talk about matrix elements. So what you do is you take these mappings and you go to the matrix elements of unitary representations of K.
Mm-hmm. Then I completely agree. Yeah, then
that works.
Agree. That works. Yeah.
I didn't want to talk about matrix elements too much.
Yeah. It's fine. Everything you've written is correct. It's just as you know, it's not a Hopf algebra. It's a compact quantum group in the sense of Vodanovich. But okay, thanks.
This tensor here is cheated because this isomorphism just doesn't work without some really extra completion. Like the factorizing ones, they're dense over here, and this is all you get.
Okay. More questions? Comments? Maybe from online people? So if someone has a question, just go for it. If this is not the case, then let's thank Michael again. Thank you. And now there's a quick break, and then there's the main seminar.